We are literally surrounded by electrical systems every single day. But what if I told you there's a hidden danger, one that can turn something as ordinary as a streetlight or a metal fence into a lethal hazard? Today, we're going to pull back the curtain on what happens when electricity goes rogue. We'll dive into how engineers protect us from these invisible threats called touch potential and step potential. So, could touching this streetlight actually be fatal? I mean, it seems like a crazy question, right? We walk past things like this all the time without a second thought. But here's the thing. Under the right fault conditions, which, believe it or not, aren't that uncommon, the answer is a terrifying yes. So, how is that even possible? Well, the whole problem boils down to something called earth potential rise, or EPR for short. You see, when a big electrical fault happens and all that current dumps into the ground, it doesn't just disappear. Nope, it actually energizes the soil itself, kind of like charging it up. And this creates two really distinct and potentially deadly hazards that we absolutely need to get our heads around. All right, so let's break these two threats down, touch potential versus step potential. Now, even though they're both caused by that same fault current hitting the ground, they're totally different animals in how they can hurt someone. Understanding the difference is super important. Okay, first up, touch potential. So picture this. An electrical fault happens and suddenly the metal pole of that streetlight is live with electricity. You, not knowing any better, go and touch it. Now, your hand is at one voltage and your feet on the ground are at another. That difference, that's the touch potential. And it creates a path for current to flow right through your body, and I mean right across your chest where your heart is. Not good. And let me be really clear here. This isn't just some crazy high voltage substation problem. We're talking about your standard low voltage system. You know, the 230 or 240 volts that power our homes and our streetlights. That's more than enough to create a fatal touch potential during a fault. It's a serious, serious risk we have to deal with everywhere. All right, now for the second hazard, step potential. And this one's a little bit weird. It's not as obvious. So when that fault current hits the earth, think of it like dropping a rock in a pond. It creates these invisible ripples of voltage spreading out. Now, if you take a step, your 2 feet land on 2 different ripples. And because they're on different ripples, there's a voltage difference between your feet. That's the step potential. And yeah, it can drive a nasty current right up one leg and down the other. You know, it's actually fascinating to see how engineers around the world tackle this. There are basically 2 big philosophies. In the US, you've got the NEC approach. Their idea is basically brute force. Create a super low resistance path, so when a fault happens, a massive amount of current flows, and bam, the breaker trips instantly. Then you have the global IEC approach, which is a bit more elegant, maybe. Their goal is to just make sure the touch voltage never gets above a safe level like 50 volts. It's like one is using a sledgehammer and the other is using a scalpel, but both are aiming for the exact same thing, keeping people safe. Okay, so we've got the what down. We know what touch and step potential are, but why do they happen? What has to go wrong for a perfectly normal piece of gear to suddenly become so dangerous? Well, it usually comes down to a few common culprits. You could have a direct phase-to-earth fault. That's where a live wire literally touches the ground or something connected to it. Or the insulation on the wires could just get old, crack, and fail over time. And then there's a really sneaky one, a problem with the protective wiring itself, like a broken neutral wire. Any of these can kick off that earth potential rise and create a really dangerous situation. Now, here's where it gets really interesting. A huge factor in all of this is the dirt under your feet. Seriously, the type of soil you're on can be the difference between life and death. Just look at this table. Damp garden soil, it lets electricity flow pretty easily. But dry, rocky ground, it's like a massive resistor. This number, the resistivity, completely changes how big that danger zone gets and how high the voltage will spike. It's a massive variable engineers have to account for. All right, that's enough doom and gloom about the problem. Let's get to the good stuff, the solutions. How do engineers actually stop this from happening? Well, the most important thing to know is there's no single magic fix. It's all about building layers of defense, one on top of the other. And we can actually think about this as a 4-step plan. It all starts with the basic system design. Then we add in protective devices. After that, we use physical barriers. And finally, we wrap it all up with ongoing maintenance. So let's peel back each of those layers. So, layer 1, the foundation of everything, is a really solid earthing system. This means we're driving big metal rods deep into the ground to get a great connection to the earth. It also means we're bonding, that is, connecting all the metal parts together. The idea is to create what's called an equipotential zone. Basically, if a fault happens, everything rises to the same voltage at the same time, so there's no dangerous difference from one spot to another. Layer 2 is all about our fast-acting guardians. Think of things like RCDs, residual current devices. These things are just incredible lifesavers. They can detect even a tiny amount of current leaking where it shouldn't, like through a person, and they shut the power off in a fraction of a second. Then you've got your standard circuit breakers. They do the job too, but for them to be fast enough, we have to make sure the fault path has super low resistance. For both of them, the name of the game is speed. The faster it disconnects, the safer everyone is. Okay, next up, layer 3, physical controls. This can be as basic as just making sure we're using really high-quality insulation on all the wires, but it also includes clever things like putting down a thick layer of gravel or asphalt around equipment. Why? Because those materials are terrible conductors of electricity. They basically add a layer of insulation under your feet, which makes it much, much harder for a dangerous current to flow. And that brings us to the final and maybe most important layer. Look, you can have the most brilliant, safest design on paper, but if you just walk away and forget about it, it's not going to stay safe. Corrosion happens, things get damaged. Safety is an ongoing job. And that means you got to get your hands dirty. We're talking about regular testing, going out and measuring the resistance of those earth rods, making sure all the bonding wires are still connected, and checking that our breakers will still trip fast enough. It's a constant process of checking and rechecking to make sure everything is still working the way it was designed to. All right, let's put all the pieces together. Let's go all the way back to that streetlight from the beginning. Now that we know all this, let's see exactly how that seemingly harmless object becomes so dangerous. So the story starts with a single fault. Maybe the insulation inside the pole has gotten old and worn through, and a live wire is now touching the metal pole itself. That pole is earthed, so now current is pouring into the ground, creating those invisible voltage ripples spreading out from the base. Okay, scene 2. Somebody walks up and just casually leans against the pole. Their hands are now electrified, but their feet are on the ground a little ways away, which is at a much lower voltage. Boom! We've just created a perfect path for electricity, and that person is experiencing a potentially fatal touch potential shock. Meanwhile, another person is just walking past, minding their own business. As they take a step, one foot lands on one of those voltage ripples, and the other foot lands on another. That creates a voltage difference right across their body. They're getting a step potential shock without ever even touching the streetlight. It's wild. So, what's the big takeaway here? It's this. Proper earthing, bonding, protection, and maintenance, this stuff isn't just about passing an inspection or following some rule in a book. It is a fundamental commitment to keeping people safe from very real dangers they can't even see. And that really leaves me with one final thought for you. As a current or future engineer, how are you going to make sure that these invisible dangers are always front and center in your designs? How will you guarantee that your work is fundamentally safe for everyone? Hey, thanks so much for watching. If you got something out of this deep dive, do me a favor and hit that like button, share it with a friend, and subscribe for more. We'll see you in the next one.